Welcome to Pharma Stability Series. If you want to understand stability studies in a simple, practical, and regulatory-focused way, you are in the right place. In this video, we will break down a key stability topic step by step, including its scientific basis, regulatory importance, and common industry expectations. So let's get started.
We all trust our medicines to work, and at the very core of every single one of them is an active pharmaceutical ingredient, or an API. We just kind of assume these things are rock solid and stable, but what if that assumption is actually a really dangerous oversimplification? Today, we're going to dig into the hidden fragility of these APIs and why it matters so much for the safety and effectiveness of our treatments. So let's just start with a really basic question. Is a pure chemical substance always stable? I mean, on the surface, it makes sense, right? It's simple, it's clean, it's not nearly as complicated as a finished drug. But as you're about to see, that's a trap in thinking. And here's the catch. Our source material points out that that exact assumption, that pure equals stable, is where all the trouble begins. It's a massive blind spot that can lead to some pretty serious quality risks down the road, turning what you thought was a stable substance into a huge liability. So here's our game plan for this explainer. First, we'll tackle what's called the stability blind spot. Then we'll dive into the invisible world of chemical changes. After that, we'll look at real-world threats from packaging and storage, unpack the human element of complacency, and finally, we'll talk about what it really means to go beyond just passing the test. All right, let's jump right into our first section, the stability blind spot. This is all about tearing down that myth that pure things are automatically stable. The thinking that gets people into trouble is actually pretty straightforward. Teams look at an API and see something that's chemically cleaner and way easier to deal with than the final complex product. So they just naturally underestimate the risk and figure, stability is a given. But the reality, and our source is really blunt about this, is that API stability fails way more often than people think. And the crucial part, these failures are almost always because of weaknesses that could have been prevented in how we understand them, how we store them, or how we control them. It's not just bad luck. It's about overlooking the details that really matter. Okay, so let's see how this blind spot actually creates real problems. On to Section 2, unseen chemical changes. Think of this as the first hidden culprit, the silent saboteur that's working away at a molecular level. So at the very heart of these chemical changes is this idea of impurity growth. An API can be perfectly fine when it's made, well within all the specs. But over time, while it's just sitting in storage, these tiny, seemingly harmless degradation pathways can start to grow. What started out as a total non-issue can literally snowball into a failure that kills the product. And what makes it happen faster? Well, this slide shows the usual suspects. Really simple environmental things like heat, humidity, and oxygen, or even tiny amounts of leftover solvents from manufacturing. All of these can act like fuel on the fire, speeding up that hidden degradation. All right, let's shift gears from the molecular level to the big physical world with Section 3, packaging and storage perils. Because honestly, a stable substance is only as good as the container it's in. I love this slide because it shows the gap between theory and reality so perfectly. On the left, you've got the ideal, climate-controlled world of the lab. And on the right, the harsh reality of a warehouse. Temperatures all over the place, moisture finding a way in, the stress of just being moved around. All of it can weaken the container's defenses. And this right here is the main takeaway. You can have the most chemically stable API in the world, but if you stick it in a package that can't protect it from what's really going on out there, you don't have a stable product. You have an unstable system. The packaging isn't just a box. It's a critical part of the whole stability equation that often gets overlooked. This brings us to what might be the most unpredictable factor of all. Section 4, the danger of complacency. This is all about the human element, where how we control our processes and how we read our data can make or break everything. So when one batch of an API is stable, but the next one isn't, it is so tempting to just call it bad luck. But it's not. It is a massive red flag. It's telling you that there are subtle differences between those batches, maybe in particle size or trace impurities or how well it was dried, and that means your manufacturing process isn't nearly as buttoned up as everyone thinks. Now this slide is a perfect little story. Just look at the data. At every single point the batch passes, the status column just says pass, 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 pass. But look closer. Do you see the story these numbers are actually telling? The purity is slowly but surely dropping, and the impurities are creeping up. The data is practically screaming that there's a problem, even while everything is technically passing. And here's the punchline. So many of these programs fail, not because the warning signs weren't there, but because nobody was reading the data with a critical eye. They just saw a bunch of passing results and figured everything was fine, totally missing the clear trend pointing straight toward failure. It wasn't a data problem, it was an interpretation problem. So, how do we stop this from happening? Well, that brings us to our final section, beyond passing the test. This is about shifting from just ticking boxes to actually building a robust scientific program. And the stakes? They could not be higher. Seriously, make no mistake. Getting this wrong has major consequences. If you can't scientifically defend your API's retest period, basically its shelf life, regulatory bodies will notice. And that can lead to your submission being rejected, painful audits, and a total loss of credibility. The solution, then, is really built on these 4 pillars. It all starts with a strong study design, right from the get-go. It requires real, robust control over storage conditions and a serious evaluation of the packaging system. And maybe most importantly, it demands a disciplined review of data trends, not just looking at isolated pass-fail results. And that leaves us with this one last really powerful question from our source. Is your stability program built on real, rigorous science that can actually anticipate and control for all these hidden risks? Or is it just guesswork dressed up to look like science, basically just waiting for a failure that was probably preventable all along? It's a question that gets right to the very heart of quality and patient safety.
If this helped, like and subscribe.